Semester 3, 3 credit hours, 48 teaching hours, paper 11. The primary goal of this course is to equip students with indirect demographic estimation methods, tools designed to derive accurate population parameters, fertility, mortality, and migration, when direct data sources, such as complete civil registration systems or reliable vital statistics, are missing, incomplete, or defective. Course overview and structural framework. Core focus: moving beyond basic direct rates like crude birth rate or crude death rate into model-based estimations, demographic dynamics, and error correction models. Core approach: each method evaluates 4 specific criteria. 1. Data requirements: what surveys, censuses, or age distributions are required. 2. Assumptions: what underlying conditions, e.g., constant fertility, closed population, stable age distribution, must hold. 3. Limitations and biases: how reporting errors, recall bias, age misreporting, impact results. 4. Evaluation and interpretation: how to adjust and interpret output parameters. Forward linkage provides the theoretical foundation for Population 652, Computer Application for Statistical and Geospatial Analysis in Semester 1 Phi. Detailed breakdown of units. Unit 1, Introduction to Indirect Techniques, 6 teaching hours. Focuses on why indirect methods are necessary in developing or data-scarce settings, and introduces stable population theory. A. Definition, need, and evolution of indirect techniques. Need: direct measures rely on 100% complete birth/death registration. Where registration is incomplete, indirect methods reconstruct measures using census or survey.
Explain Unit 1 and 2 in detail.
Here is a comprehensive breakdown of Unit Y and Unit 2 from the Population 601 syllabus, covering their theoretical foundations, key assumptions, mathematical logic, operational procedures, and practical limitations. Unit 1, Introduction to Indirect Techniques, 6 teaching hours. A. Definition, need, and evolution of indirect techniques. 1. Definition and core concept. Indirect demographic techniques are analytical methods used to estimate fundamental population parameters, such as total fertility rate, TFR, infant mortality rate, IMR, expectation of life at birth, E_0, or net migration, using incomplete, defective, or non-traditional data sources. Unlike direct estimation, which calculates rates by dividing reported events by person years at risk, e.g. CBR equals frac registered births mid-minus year population times 1000, indirect methods rely on retrospective summary questions asked in single-date censuses or sample surveys, e.g. how many children have you ever born? Demographic models, e.g. model life tables, stable population models, to convert non-standard proportions into standard rates. 2. Need for indirect techniques. Absence or incompleteness of civil registration and vital statistics, CRVS. In many developing countries, vital registration systems fail to capture a significant percentage of births and deaths. Recall and omission biases. Survey respondents frequently underreport recent events, e.g., deaths in the past 12 months, due to memory lapse or cultural taboos surrounding deceased infants. Age misreporting and digit preference. Systematic reporting errors, e.g. heapings on ages ending in 0 or 5, distort direct age-specific rates. Cost efficiency. Census summary questions are significantly less expensive to implement than continuous, universal vital registration systems. 3. Evolution of indirect methods. Early foundations, 1900s to 1950s. Alfred Lotka established stable population theory, demonstrating that constant age-specific birth and death rates produce a constant age distribution. The breakthrough, 1960s to 1970s. William Brass pioneered indirect estimation by utilizing parity data, children ever born, to estimate child mortality and adjust fertility reporting. Standardization, 1980s. The United Nations published Manual X, Indirect Techniques for Demographic Estimation, 1983, which standardized algorithms using Coal-Domini and UN model life tables. Modern developments, 1990s present. Extensions by Trussell, Feeney, Poloni, Heligman, and Arriaga adapted these models to handle changing demographic regimes, e.g., declining fertility or mortality, and inter-survey evaluation. B-stable and stationary models. 1. Theoretical concepts. Stable population model. A population subject to constant age-specific fertility rates, F_x, and constant age-specific mortality rates, μ_x, for a long period. It develops a constant age distribution C of x, and grows at a constant intrinsic rate of natural increase, R. Stationary population model. A special case of a stable population where the growth rate is 0, R equals 0. Births equal deaths, and the age structure x is directly proportional to the survivorship column L of x of a life table. 2. Fertility estimation from proportion under age 15 and survivorship, L_5 or Q_5. Closing parenthesis. When CRVS data is absent, a stable population model allows demographers to estimate fertility indicators, like crude birth rate or total fertility rate, using two accessible inputs. 1. C15, the proportion of the population under age 15 obtained from a single census age distribution. 2. L_5 or Q_5, the probability of surviving to age 5, derived from child mortality estimation methods. Operational procedure. 1. Identify C15 and Q_5. Calculate C15 equals frac population under 15 total population. 2. Model matching. Compare the observed C15 and Q_5 against tabulated stable population parameters, such as the Coyle-Domainy model stable populations. 3. Derive growth rate, CAS-ENOL, and birth rate,